announcements real quick, and then a couple of notes here for registration as well. So this week in lab, we're going to be doing experiment 10 and 11 are what is on your syllabus. The actual doing, for the most part, is experiment 11. Experiment 10 tells you about gas chromatography, which we're going to go through here in a little bit. But the actual doing is in experiment 11. You're going to be using your alcohol that you made last week in the Grignard experiment for experiment 11. So remember, your pre-lab for experiment 11 should be specific for the alcohol that you made in 8, whatever that is. So you should have a specific experiment 11 pre-lab, not a generic experiment 11 pre-lab. Okay? Now, a quiz this week. Your experiment 7 report is due. You're going to turn this in your notebook, like experiment 3 and experiment 1. One thing, there's multiple things in your lab manual to keep in mind for the report, but one thing to keep in mind is note the average number of repeat units of your polymer that you're analyzing from the GPC data that you got. Next week we'll be doing experiment 12 on the syllabus. It says experiment 12 and 13. The actual doing is in experiment 12. And then in 2 weeks, your experiment 8 and 11 report will be due. That is worth 75 points because we're combining 2 experiments together in one report, but because they are related, you use the product from one to go on to the next one. We're putting them together in one report. One thing you want to do, though, is keep your pre-lab for experiment 8 and 11 and the experimental for experiment 8 and 11 separate. Keep them on separate notebook pages, okay? So don't have experiment 11 just follow in where you left off with experiment 8. You want to keep things on separate notebook pages and treat them like separate experiments. You will write a common conclusion, though, for both of the experiments when you turn in the report. So there'll be one conclusion, but 2 pre-labs and 2 experimental. For registration this week for Chem 256A and 256B, I wanted to clarify a little bit. So I was talking last week about Dr. Valdez's section on Thursday, Chem 256 5A. That section is for people who are only taking Chem 256 A portion, not the B portion, because there is no B portion to that lab. Now that doesn't mean that you can't take another, so if you've decided you are only taking the A portion, you don't have to take Dr. Valdez's lab. You can also take the A portion in the other 4 lab sections, okay? But if you register for Dr. Valdez's lab, you want to make sure you don't want the B portion, okay? So the people that are in Dr. Valdez's lab, make sure you don't want to take Chem 256B, all right? You're not limited to which Chem 256A you can take, all right? But you just don't want that lab section if you're going to take 256B. The other thing is, like I was saying last week, when you go to register, if the lab section that you need, not want, but need is full, make sure you email me with the reason why you need that particular lab section, and then also make sure that you get yourself on the wait list for that lab section, because I can't do anything in the wait list process if you're not on the wait list. I can't help you get into that section till drop add if you don't put yourself on the wait list. Okay, so do those 2 things. Email me, put yourself on the wait list. Okay. So a couple of notes here from experiment 8 before we get into experiment 10 and 11, okay? So experiment 8, a lot of you will need to do the fractional distillation to purify your alcohol. And that can happen in lab before you start experiment 11. The one thing that's really key is know the boiling point of your alcohol, okay? And the atmospheric boiling point, not the under vacuum. So it should be greater than 100 degrees. If you have a boiling point that is under vacuum, so it's under 100 degrees, in the Aldrich catalog you can use what's called a nomograph, and it can help you figure out what that atmospheric boiling point is based on the pressure it was collected, okay? So you want to look at a nomograph to translate things from vacuum boiling point to atmospheric boiling point, okay? So we all were making in all the combinations of alcohol or alkyl bromide and aldehyde that you guys used last week, you were in the end making 4 different compounds through all those combinations, okay? And so you were either making a 3-heptanol or a 3-octanol. That's what this guy would be. R is H for the heptanol or CH3 for the octanol. Or you are making a 4-heptanol and 4-octanol. So the boiling point of the heptanols should be somewhere in the 150s. The boiling point of the octanols should be somewhere in the 170s, okay? So make sure that that's what you're using for your fractional distillation. You want to start collecting with that fractional distillation about 10, 20 degrees below the boiling point of your alcohol, okay? And you don't care about the rest of what boils and distills over before then. You only care about getting your alcohol fractions, okay? So you don't need to be taking fractions all the way up to 130 or 150, depending on what your alcohol is. You just need to worry about that 10 to 20 degree range around your alcohol, okay? And usually below it. Yeah?
Can you do something with the nomographic score?
If you can only find a vacuum, under vacuum boiling point, then you would use that to go from vacuum boiling point to atmospheric boiling point. And those we can show you in the lab before you do the fractional distillation. We can show you how to use that. So just make sure that you don't need to take 5, 10 fractions from this distillation. You only need the fractions that contain your alcohol product, okay? So you don't need everything that comes off before that alcohol product. So just start collecting alcohol 10 to 20 degrees below the boiling point of your alcohol. Okay, so let's talk about experiment 11 first, what we're going to be doing, and then we'll talk about gas chromatography. So experiment 11 is going to involve an elimination reaction. We've already talked about one of those. Now we've got a different type, which ties in really nicely with what you're doing in lecture and going to be tested on this week in lecture. So we've got our alcohol. We're putting it in sulfuric acid, so a strong acid, okay? And by doing that, we're going to end up protonating our alcohol. So we've got protonated alcohol here. And then here, just remember, we'll get back to here, but remember this is a CH3. So just keep in mind that we've got a carbon with 3 hydrogens there, because that will come into play here in a minute in the mechanism. So then we're going to, it's really easy now to lose water. A big driving force for this reaction is we protonate the alcohol and then we can lose water, and in the process that will cause the elimination reaction. And so our conjugate base of our acid, in our case we've got H2SO4, so conjugate base is HSO4 minus, will help us then cause deprotonation to cause the elimination reaction, okay? And so we've got our HX minus here. So we gotta, to be able to show everything, I gotta draw all these protons in to show what's going on here, okay? So we, got the plus there. And here comes picture so we can see what's going on. So we've got the loss of water here, which is causing, now we've got a carbocation, in this case a secondary carbocation, and then we can use our conjugate base to lose one of these protons to then cause the double bond, and it can come from either direction, okay? So we can lose a proton here, we'll form a double bond here, we can lose a proton here, we can form a double bond there, okay? So we can either form our 1-heptene, so loss of a proton here, or we can form forms of our 2-heptene, and so we form cis and trans 2-heptene. Here we don't have cis and trans because we just have 2 protons here. We don't have 2 different things on this end of the double bond, okay? So does everybody see how that happened? Okay. So it's from this guy here can come in and take a proton here, or can take a proton here. I'm just not drawing all of the arrows because it gets a little bit messy figuring out where things are going, all right? And whenever you form trans, keep in mind too, whenever you're forming the trans product, you're also going to be forming some cis product. Even though we know trans is favored, you're always going to have some cis product, okay? The other thing that can happen, and so I told you this is an elimination reaction, it's an E1 mechanism. Does anyone know why it's E1?
It's rate independent.
Versus E2?
Rate independent.
We got an intermediate, right? So it's going to be E1. This intermediate can rearrange. So we can get a hydride shift too. So this makes things even more complicated with the number of products you can get. So we've got, if we look at our intermediate here, where we form our carbocation, if we draw all our hydrogens on there, and we've got our carbocation that formed here, what we can do is a hydride shift, and we can move that carbocation. And so we could move the carbocation here. And so you could get this carbocation that then could form a double bond here or form a double bond there, okay? Now what do you know about carbocations? Where are they going to go?
Most stable.
You want to go to the most stable carbon, right? Okay. So in this case, we're not going to move from here to here, right? We wouldn't go from a secondary carbocation to a primary carbocation, okay? So you're going to move either to an equal carbon or something that's even more substituted. So you want equal substitution or more substitution with your hydride shift, all right? But you're not going to move backwards to less substitution, okay? And that will give you greater stability of that carbocation, okay? So from this guy and this guy reacting, we then could possibly have maybe some product here. We could have our cis and trans 2-heptene, which would still form here. We could also get cis and trans 3-heptene, so we get a whole mixture of possibility of products, okay? So keep that in mind for your reaction as well. So related to this with our carbocation, what does Zaitsev's rule say? Remember?
The double bond forms at the most highly substituted carbon.
Right, you're going to get a double bond at the most highly substituted carbon, okay? So here, we really don't have a difference here. This was an equivalent hydride shift. We're going to get a secondary alkene, secondary alkene, but here, having this terminal alkene would not be favored over this alkene, right? And so that's Zaitsev's rule. It's just talking about the most highly substituted carbon where that double bond is going to form. Yeah.
Is that heptene or hexene?
Should be heptene. 1, 2, 3, 4, 5, 6. Whoops. Here.
Okay, sorry.
We'll add some more carbons to them. There we go. Sorry. But you're always, with Zaitsev's rule, just remember it's talking about the most highly substituted carbon, okay? So this is kind of key for when you're writing the conclusion for this experiment too. Just keep in mind what Zaitsev's rule tells you versus the favoring of trans versus cis, okay? So Zaitsev's rule does not tell you that trans is going to be favored over cis, okay? That's something different, all right? So you need to keep this in mind, but you also need to keep in mind that trans versus cis alkenes usually will see more trans than cis, okay? So kind of two different things you got to keep in mind here, all right? But then, like I was saying, remember whenever there's trans, there, even though it is more favored, you will still see cis, okay? So when you're analyzing your data, don't think that you'll only have trans alkene in there. You're going to have cis in there somewhere, okay? Now, with this elimination, we're using sulfuric acid. And so what we're doing is we're setting this up to favor elimination. Okay? And the reason for that is with the sulfuric acid. Okay? So H2SO4, its conjugate base is HSO4 minus. Okay? This is not a good nucleophile, and that's really important, okay? It gives a weak base, and it's not a good nucleophile. That is important because we want it to only give elimination. We don't want to see substitution, okay? And so if we use HCl, its conjugate base is Cl minus. Now what can you say about it being a good or bad nucleophile? It's a good nucleophile, right? So with this guy here, you would also get substitution besides elimination. So we don't use HCl for that reason. That's why we are using sulfuric acid, okay? Now the thing is we're using the same sulfuric acid that you used last week. It's that 9 molar sulfuric acid. So again, be careful with it just like you were careful with it last week. This week we're using a whole lot more of it. You're going to need 50 milliliters of it. So be really careful handling it. And this week, unlike last week, we're going to heat it up to boiling. Okay? So be careful handling it. All right? So what you're going to get with this mixture is you're going to have the alkene. Actually, sorry. We're going to start with our alcohol. So we're going to use all of our fractions of our alcohol that we think have products in it, plus the 9 molar sulfuric acid. Okay? What we're going to use is what's called a steam distillation, okay? So you're going to get this whole mixture heated in a simple distillation apparatus, and you're going to get it distilling, okay? And so the boiling point, we've got a mixture here, so your boiling point is going to be depressed from either one of these guys, okay? So your boiling point is going to be less than each component individually. And what you may see is like your alcohol, definitely below your alcohol boiling point, and then you're going to see as it's boiling over, you're actually forming your alkene. So when we're talking about what's actually being distilled, it's your alkene that's being distilled, okay? So the alkene and still the sulfuric acid are distilled together, okay? And so that, this co-distillation with this aqueous portion is what makes it a steam distillation. So they're distilled together, or you could say that they're co-distilled. When you set up the apparatus for this distillation, you're going to set up a regular simple distillation, but your collection flask, instead of a flask at the end, is going to be your 25 milliliter graduated cylinder, okay? The reason that you want that is you want to be able to measure the volume of what's being distilled over. So you're going to have this mixture that's going to come over when it's hot all together, but as it cools, you're going to get a separation of 2 layers, okay? And so you're going to have your alkene layer, and then you're going to have this acidic aqueous layer, okay? And so you're going to watch in your graduated cylinder for these 2 layers distilling over, and you're going to stop the distillation when all the organic layer is done distilling, okay? So when that organic layer is not growing anymore in volume, then you can stop the distillation, all right? And sometimes what it takes is actually a lot of the organic layer will come over first, but you can't really see the aqueous layer, so you may have to distill a little bit extra to make sure that you're looking at the top layer and not the bottom layer. Get a little aqueous layer in there to see it, okay? So your alkene based on densities should be on top, your aqueous layer should be on the bottom. Once that top layer is not growing anymore in volume, then you can stop the distillation. So you're not going to distill over all 50 mils of water or of acid. You're only distilling until you're done forming that alkene, okay? Then let it cool very slowly, okay? We don't want to take this apart while it's hot. So let everything cool slowly, let everything that's dripping into that grad cylinder just stop dripping. Remember that all of that glassware is going to have acid throughout it, so be careful when you take it apart. You handle it with gloves. And rinse everything very carefully. The other thing is be really careful because you're not going to have a lot of alkene product. You'll have like 4, 5, 6 milliliters of product, and you don't want it to spill and lose all your alkene, okay? Because that's basically 2 weeks worth of work that you don't want lost on the bottom of your hood, okay? So be careful with what's in that grad cylinder. Do not spill it. Once you can start taking things apart, you're going to separate what's in that grad cylinder in your separatory funnel, so be really careful using that. Make sure the stopcock's closed on the separatory funnel. Don't let it all drain through onto the bottom of the hood or anything like that. I'm saying all this because it's happened before, so that's why, usually why I give you helpful hints, because it's happened before. So you'll drain your aqueous layer. Then you're going to wash that organic layer with sodium bicarbonate, and you use, 10 milliliters. You don't need very much because you've got a really small layer. And then you're going to go on and dry that organic layer with magnesium sulfate. But remember, you don't have a lot of volume, and so you don't want to use a lot of magnesium sulfate, okay? You have that pure alkene layer that you're drying. You don't want to have to add any solvent to it, because if you do, then you'll have to go through and do a simple distillation to remove the solvent, okay? So only use what mag sulfate that you need to dry it, and don't make pancake batter out of it, okay? Now, since you have such a small amount, and you should be using a small amount of magnesium sulfate, we're going to use this apparatus from experiment 9 to actually filter the magnesium sulfate off, okay? So what you're going to want is a clean, dry vial that your alkene product is going to go into. I recommend knowing the mass of that vial too, because then you can easily figure out your yield. Then you're going to take your flask that you have the magnesium sulfate and your product in, and you're going to pipette from that flask into this filtering pipette that will then drain into that vial, okay? So what you're going to do is just put a little piece of Chem White in the bottom of that Pasteur pipette, and then you're going to let the mixture that has the magnesium sulfate pass through here, filter all that solid out, and so what you get in here should be minus any solid, okay? So make sure you don't have any solid in here. If you have solid in here, then you need to filter it again. Once you're done filtering, these filtering pipettes, we're going to end up disposing of them. There's nothing else we can do with them once you've got the Chem White in there, okay? So once you're done with this pipette, rinse it well with acetone into your organic waste, and then in the reagent hoods, there's a beaker to collect these pipettes, okay? So we're gonna stick them in that beaker for a little while, get all the fumes off of them before we stick them in the glass waste, otherwise our glass waste will be really stinky, okay? So once you're done using it, rinse it with acetone, then stick it in the correct beaker in the reagent hood, all right? So this is the only reason you have experiment 9 in your lab manual, is for this picture, okay? So that was your contribution from experiment 9, okay? So then you need to take care of making sure you have all the data collected for experiment 8 and 11, okay? So both experiment 8 and 11 products you're going to need a yield. So before you make a GC mass spec or GC sample or IR sample, you need to make sure you have a good yield. You want to collect the IR spectrum. And then you're going to make a GC sample. And I'm going to talk to you here in a little bit about how to do that, okay? So both 8 and 11, you need each of these 3 pieces of information gathered, okay? One for your alcohol product, one for your alkene product. So make sure you get all this before you leave lab this week, okay? Now with the IR spectrum, when you write up your report for experiment 8 and 11, I was talking about experiment 8, the literature spectrum you're going to compare it to. You also need a literature spectrum for experiment 11. So you want to try and find an alkene that's very similarly related to one of your predominant alkene products for that literature spectrum, okay? So the alcohol and the alkene, you also want to find literature spectra for those. For your pre-lab for experiment 8, make sure you show all the possibilities for products when you're drawing out your reaction scheme. Make sure you draw your cis and trans products that are possible from your alcohol that you're using too. Okay? Now, once everything's cooled down slowly, then we need to get rid of, we've carefully taken apart all the glassware, get all that rinsed out. We have this distillation pot that is probably black or probably dark brown by now, that still has a lot of acid in it, okay, and a little bit of organic left in it, okay? What we're going to do is take that distillation pot, once it's cooled to room temperature, you're going to pour it into your largest beaker of water, okay? Like 2/3 full of water. Okay? Then you're going to pour it down the sink in your hood with lots of water. You're going to run the water. Just be careful handling it because, again, it has all that acid in there. And so you don't want to get to the end of your experiment and then that's when you end up having trouble with the acid and spilling it on yourself, okay? So be really careful handling it. Make sure it's cooled completely to room temperature. pour it into the beaker of water, and then pour it down the sink with lots of water, okay? It does not go in the organic waste container. Make sure it does not go in the organic waste container. Strong acid and organic waste do not mix, okay? So we do not want it in the organic waste containers, all right? Now the other thing is, in your lab manual it tells you if you were lucky enough to get 2 grams of product or more, you have to do a fractional distillation after experiment 11. You do not need to do that, okay? So you need to do the fractional distillation after 8, but you do not need to do it after 11. What would happen by doing that is you're going to change your cis and trans isomers, okay? Because those isomers and what is formed is a thermodynamic process, okay? So you will, by heating it, you'll get the thermodynamically favored isomers, which would be the trans isomers, over the cis isomers, instead of getting what initially your product mixture is and what was initially formed from the reaction. So it'll skew your results to do that distillation, then sample it for GC. You won't get what actually just came out of your reaction, all right? So don't do that last distillation. So when you're done this week, you've got your alkene product. Make sure you get your yield, IR spectrum, GC sample of both 8 and 11 products, and you've taken care of your apparatus and getting everything cleaned up. Then just store that alkene product, and if you have a little bit of alcohol product, make sure you store that as well. Okay. Okay. Questions with that before I go on to gas chromatography? Yeah.
I just wanted to verify, so for our pre-lab, that's basically done on experiment 11 only?
Yes, yeah. Yeah, you can show like the filtering, you know, what you use, your new apparatus will be filtering with that pipette, but you don't have to draw like a GC as a new equipment or anything like that in your pre-lab. Okay. All right, so now let's talk about gas chromatography, okay? And actually here, while we're at the GC sample, let's just talk about what you're going to do with these. So look at your alcohol and your alkene, okay? As long as there is no solid present, so make sure that you don't see any solid, no visible water present, because water kills the GC column. Then what you can do is take 1 drop of the alkene or alcohol, put it in a GC vial, and fill to neck with pentane. Okay? So you got to make sure that there's no solid present, no water present. Both of those will kill the GC column. Okay? And then you're going to cap it. Be careful with these caps. You don't want to tighten them too much. Okay? So if you tighten the GC vial and you see there's a septum in these vials, if you see it dimpled, it's capped too tightly. Okay, so you want it capped enough that your sample's not going to evaporate before the sample's run, but you don't want it so tight that you actually see a dimple in it. Okay, then you're going to label in Sharpie with initials and notebook page. So similar to what you did with experiment 7, if you made that sample. So you know, something like that, okay? And then you're going to put the sample in the sample block. And then fill out this sample sheet too. Okay, so you're submitting 2 samples for GC, experiment 8 and experiment 11. Make sure you get them in the right slot. On the sample sheet, there's a column for experiment 8. On the sample sheet, there's a column for experiment 11. Make sure you have the right sample ID in there. And then on the sample blocks, there's 2 rows, okay? So experiment 8 goes closest to your desk number. Experiment 11 then is right next to experiment 8. So don't confuse who is who, all right? And then as we collect the samples and get the GC data, then we will get that back to you. But it will take, to run all of the samples plus all the standards that need to be run, it will take all pretty much until like next Monday to get all these samples run and get data back to you, okay? With the GC constantly running. So we just hope that the GC doesn't stop, because then it'll be longer, okay? So we'll let you know when we have the GC data. The other thing you're going to get from your instructor is a list of standard retention times, okay? So that's how you'll analyze your data, is based on those standard retention times. It shows you a list, in that list, how cis and trans isomers are related to each other, how their what their retention times are in relationship to each other, and how positional isomers are related to each other. But we can't possibly run all the standards for every possibility that you'll have in your GC data. So from those standards, you're going to have to do a little bit of interpretation of what the other peaks in your GC data are, okay?
For the alcohol, when we're making the GC sample, do we use the pure component or the combination?
Use your purest fraction. Same with the IR, I just use your purest fraction. Okay. All right, so now let's talk about gas chromatography. And in a minute, you'll see what I mean by retention time. So we've already talked about one type of chromatography, that was gel permeation chromatography. Now we're talking about gas chromatography. So that has to do with what the mobile phase is. So our mobile phase is a carrier gas. The stationary phase is this polymer support in the column. So remember, with chromatography, there's always mobile phase, always a stationary phase. And this polymer support does not degrade with heat, which is important because we're going to heat things up pretty quickly, okay? So here's kind of schematic from your lab manual, and then also a picture in your lab manual is also a picture of the GC that we're going to use, okay? So what happens is you've got your sample. It is going to be injected into the instrument. So we've got a big auto sampler that's going to inject this, hold all of our samples on there, and as it runs each sample, it injects the sample into the instrument. That injector is hot, okay? And it vaporizes the sample. So you right away it goes into the instrument basically as a gas, okay? Then it gets into this column, which is this really tiny, tiny column. We'll show you in lab this week what one looks like. It's called a capillary column. Very tiny column. After it gets past the injector, so it's vaporized, gets onto the column, then the column isn't hot yet, okay? It starts out cool and then ends up getting hotter, all right? And so then that sample cools back down. But as it gets hotter and hotter, things that are more volatile will go back into the gaseous form more quickly. The things that are less volatile will become gas later on, okay? And so what happens is you're separating based on volatility or basically based on boiling point, all right? So things get vaporized, get onto the column, then they're traveling through the column, and as it's being heated, they are going either faster or slower based on have they been volatilized or not, all right? And this column in the instrument, it doesn't look like it's that big, but it's actually, this column is wound up into a loop. It's like 29, 30 meters long. It's a really long column that's passing through, okay? Then as it comes out of the column, then it goes into the detector, and so then it analyzes what comes off that column and when it does come off, and then it goes into the data system and your data is printed out. So what the information we're getting out from the detector is when a sample comes off and what that retention time is, okay? So we're gonna go through these parts of the GC. So this is kind of side view of a column. You've got this outer coating, and then you've got this polymer on the inside of the column, and then the actual sample is passing through the middle. So it's really, really tiny column, and there's actually layers to it. So where that sample passes through is really, really, really tiny, okay? So here, we've got this mixture that came from the injector. It was all vaporized. And then as it goes onto the column, it starts cooling. And so you get this vapor-liquid equilibrium between what has become gas and what is going to stay a vapor. And so the less volatile stuff is going to stay on the column longer. The more volatile stuff is going to pass through more quickly, all right? And so then as the column is heated up, then the less volatile stuff will also volatilize as well. So we're separating based on volatility, and in our case, it's pretty much, for the most part, volatility because our column is relatively non-polar, so you're not going to see any difference also based on polarity. So this, i.e., it's separated on boiling point, okay? So low boiling compounds elute first, or come off the column. When I say elute, that means coming off the column. And then the high boiling compounds elute later. Okay, so GPC we're separating based on size. Here we're separating based on boiling point. Okay, so if you have a list of compounds and their relative boiling points, you can pretty much figure out what the order is going to be based on that boiling point. Okay, now with this capillary GC, so we've talked about separations with boiling point and using fractional distillation. Our alkenes have such a close boiling point to one another, we can't separate them based or we couldn't use a fractional distillation to separate out each individual alkene. So that's why we have to use GC. So this capillary GC, you're going to get a separation of compounds that vary only a couple degrees in boiling point. And so that's how we can analyze a sample and decide what is the alkene mixture, is by using the GC. So we've talked about the injector, we've talked about what happens on the column and the heating on the column, and we have, like, the column stays at a certain temperature and then slowly is ramped up to another temperature over time and then has a finishing temperature that it stays at to finish the run. And you'll be able to see that on the front of the GC. I'll show you here in a minute what you're going to use to look at on the front of the GC. But our This, first of all, sorry, is the injector. So we've got our sample comes in here, and then we've got the carrier gas that's being fed into the injector. This is really hot, and then we've got, it comes out of the capillary column, into the capillary column. Okay, so that's what happens right when your sample is injected. And this is, in your lab manual, it gave you some common GC columns and what is in their stationary phase and what you use it for separation. So there's specific columns that you use for specific types of separations. We use a column that is can be used for a wide variety of compounds because we use this column for experiment 8 and 11. We also use the same column for experiment 14. So it's a pretty broad spectrum column in that what kind of compounds you can put on there, okay? But here's what the detector looks like, okay? So it's called a flame ionization detector, or an FID. This is a really sensitive detector, and so that's why we use it. So what happens is you've got your sample coming into this detector after it came off the column, okay? You also have hydrogen gas mixing with that sample, okay? And then you also have some air coming in too. As that sample goes through, passes through, mixes with the hydrogen gas, then it passes into this flame. So we basically char the sample, but in with that flame, we've got kind of an electrospray. You're making ions out of what is coming off that sample, okay? You're giving it charge. And based on doing that, then we collect here on the ion collector those fragments that came off in the flame and then were ionized and end up collecting above that flame. So you go through and you've got this igniter and polarizing electrode that's kind of making this electrospray of your product, okay? So then what is detected is those ions, okay? You're detecting current from those ions coming off of the detector, okay? And you're detecting how much and then also when it comes off the column, okay? But this makes it really, it's a really sensitive detector. So what you're going to want to copy off of the front of the GC is this table. You want to make sure you put it either in experiment 8 or experiment 11. It doesn't matter which, because you use the same conditions for both experiments, but you want to copy all of this information off. So this table is on the front of the GC and it's filled out for experiment 8 and 11, all right? So you've got information like about the column length, diameter, stationary phase, film thickness. What is the injector temperature? What's the detector temperature? So the detector is also hot as well. The column oven program, you know, what temperature do you start at? How long are you at that temperature? Then how fast you increase the temperature, then your final temperature, final time. The carrier gas and what is the flow, and then the split ratio in the injector, and then volume of sample that's injected. So all of these components determine how things are going to come off of the GC and determine the order and retention times, okay? Yes?
Should that table just be after like our reagent table in our pre-lab?
You can put it in the experimental of either experiment 8 or experiment 11. So it doesn't need to be in the pre-lab, it can be in the experimental portion. Just make sure it's in one of them, since you're turning in the notebook for both of them, okay? But you want to make sure you get all this information, then also think about what changing these things would do to changing what happens with the GC and how it would change the retention times of how things come off the GC, okay? Because that's part of understanding what's going on with gas chromatography. So this is an example of GC data that you will get. You will actually get 2 pages. So you're going to get a peak list. So it's all the peaks that came off. And you'll get the retention time, the start retention time, the end retention time. This is the average retention time that you record. Then a bunch of information about peak height and peak area. And then what percentage of the total was that peak, okay? Then the second page is going to be the actual chromatogram. What does it look like when your sample came off the GC? Okay. So I've kind of combined both of those into one so you can see the table that you want to record in your notebook, okay, and what you're going to want in your report for both experiment 8 and experiment 11. So you're going to make sure you include in your report, you're going to have your GC data for experiment 8 and 11. You're going to attach that to your notebook when you hand in your report. But this table is also table 10.2, so it's in experiment 10. You want to have a column for standard retention time. You want to have a column for the retention time off your data. So this is the standard retention time that you get from your lab prof. This is the retention time from your data. You want to give the area and the percent area. Okay, so peak area and percent of total. And then you want to give the identity of what each of those components are, even if you don't have the standard retention time. Okay? So like I said, from the standard retention times, you're going to have a set of retention times, but not every alkene possible, okay? You'll have the 4 alcohols, but you won't have every alkene possible. So you have to do a little bit of playing with the puzzle to figure out who is who based on the trends that you see. The other thing to keep in mind, that something that will come off in the GC, but you don't have a standard retention time for it, is your alcohol can actually oxidize to form ketone, okay? That ketone comes off at a very slightly lower boiling point than your alcohol. So it's going to come out at a faster retention time than your alcohol, right before your alcohol. So one way to figure out if that's ketone or not, besides seeing a peak that looks like maybe your alcohol but doesn't have quite the right retention time, is you should see it in your alcohol GC and your alkene GC. It's not going to go away between the two of them, okay? So between the two GCs, you should see alcohol go away, alkene be formed, but that ketone peak won't disappear. There's nothing you do in experiment 11 that makes that ketone disappear, okay? The other thing to keep in mind when you're analyzing all this data, your IR data, your GC data, keep in mind what evidence you have for going from experiment 8 product to experiment 11 product. You've got a lot of comparisons you can make between the data, both with the IR and the GC, that shows that you made product, okay? So keep that in mind with your analysis. Okay, questions you guys have?